In this video, we're going to take a look at Le Chatelier's principle with respect to gaseous equilibrium systems, and we're going to take a look at how changing the pressure of these systems impacts how the system will respond. So the questions, this is our reaction. So we have A, which is a solid, plus 2B, which is a gas, gives you C and 3D, both being gases. And the question states, at equilibrium, a 3-liter container has 6 moles of B, 3 moles of C, and 24 moles of D, and 1 mole of A. So I want you to calculate the K for this reaction, and then we're going to make changes to it later and see how it compares to K and how it's going to get back to it, and we're going to quantify these concentrations. So writing the expression for it. So for gases, if you're representing the concentrations in molarity, we write Kc. If we were representing them in pressures, we'd write Kp, but that's different. We're just going to look at this for now. So we, again, for any K expression, we're going to write our product concentrations in molarity over our reactant concentration in molarity, and we're going to raise those values to the power of the coefficients listed in the balanced chemical equation. So for this case, I gave you a 3-liter container, so I didn't give you initial molarities, I gave you initial numbers of moles. So the first thing you would have to do is calculate the molarities, which is moles per liter. So if we have 1 mole of A, that's in a 3-liter system, that's going to be a third of a mole. Okay, we had 6 moles of B, so over a 3-liter container, that's a 2 molar concentration. 3 moles of C in 3 liters, that's 1, and then 24 moles of D in 3 liters, so that is a molarity of 8. So when we plug in those concentrations to our K expression, we get a value of 128. This tells us the reaction is very product favored. If it's much greater than 1, you would say it's product favored. If it's much less than 1, you would say it's very reactant favored. So then, what we're going to do is we're going to calculate what our concentrations are initially if we alter the pressure. So the way we can do that, if we're going to reduce the pressure by doubling the volume of the container, what that's going to do is it's going to make all our molarities get cut in half, right? Because molarity is moles per liter. If you're doubling the number of liters, your molarities get cut in half. So Q, or that ratio of product to reactant at any point in time, we just take our molarities from the first system and we divide them by 2. So we go from 1 to 0.5, 8 to 4, and 2 to 1. And when we calculate the value of Q at this point in time, we get a value of 32, which is significantly less than K. So what that means, our product to reactant ratio is lower than it will be when it reestablishes equilibrium. So we know that the reaction is going to favor the forward direction. So on a test, I could ask you to set up an ice chart to represent what's going to happen, but I wouldn't actually have you calculate X, but for the sake of this video, we actually did. So here's our ice table. Okay, so we have our reaction, and we leave A out of the expression because it's a solid. I should have said that earlier. So we don't worry about that, and I'm going to tell you we actually have enough for this reaction to proceed. So we write our concentrations that we have initially once the equilibrium is perturbed, or once we basically double the volume of the container. So we plug those molarities in, and then we take a look at how those molarities are going to change. Now, we said the reaction is going to go in the forward direction, so that means we're going to be adding product, and we're going to be losing reactant, but we don't know how much, and that's what we're going to set this up to figure out. So let's take C, because it has a coefficient of 1, and say that it's going to go up by X. So for every 1 mole of this that we gain, we're going to use 2 moles of B. So this will go down by twice that value. And this, because it has a 3 to 1 ratio, it will go up by 3 times as much as C. So we plug these in for our changes. And then at equilibrium, we're going to have our initial amounts, apply the change to it, and that's going to be our concentrations at equilibrium. And if I were asking you to do this, I would just have you leave it in this state, because I'm not going to ask you to calculate X in this complex algebra. So, but if we were to do it, we would find that X is 0.16. And then we can go back and check to see if we were right. Because if I apply that as my X value, and I plug that in, these numbers in black represent what our equilibrium concentrations would be once we plug in 0.16 for X. So at equilibrium, we would have 0.66 for component C, 4.48 for D, and 0.68 for component B. When we apply the exponents, we actually get that the value is 128, and we can say that we've reestablished equilibrium. So we know how much of the products had to form, we know how much of the reactant got consumed, and we now know what we have once we've reestablished equilibrium.